Hello, class. So
Hello.
today, oh, so Natalia, you can hear me, right? Awesome.
Yes, and I can hear you. Yes.
Yeah. So today we plan to cover. Yeah, thank you. Hello, Ashley. Yeah, so today we plan to cover 11.4, some basics about probability. So probability has different definitions. We only cover two of the definitions. The first definition is the theoretical probability. The second definition is the empirical probability. So let me write it down. The other is empirical. Theoretical probability is also called the classical probability. And I want to introduce what is classical probability model. To be a classical or theoretical probability model, we have the following two conditions need to be satisfied. The first condition, the sample space of the model has a finite number of outcomes. An outcome is the result of an experiment. Experiment is a process that we will not know what's the without a certain result. Second condition is those finite number of outcomes are equally likely to occur. For example, if we consider this experiment, rolling a die. Rolling a die is an experiment because we are not sure about the result. The result could be number 1, could be number 2, or 3, or 4, or 5, or 6, right? We know it's going to be one of those 6 results, but which specific result we are not sure. So that's an experiment. And this experiment has sample space. Sample space is a set containing all the outcomes. So this experiment has 6 outcomes in total. We either get number 1 or 2 or 3 or 4 or 5 or 6. And it has a finite number of outcomes. And all the finite number of outcomes are equally likely to occur. They are equally probable. They are equally probable because the die, we assume the die is fire. Each side has the same weight, then they have the same chance to occur. And event is another important definition. Event is a subset of the sample space. Okay, event is any subset of the sample space. For example, if we use capital letter A, B, C, D to represent the event. If we let A be, we roll a die and get an even number, then we are able to describe the event A as a subset of the sample space. containing 2, 4, 6, 3 different elements. A is a subset of the sample space S. A is an event. Okay. In my video, the concept of classical probability model is explained in more detail. So how do we compute the probability if the model is a theoretical probability model? The formula is K over N, is a fraction. Probability must be less than or equal to 1 and bigger than or equal to 0. So when we find the value of the probability of a certain event, we have to look for two numbers. One number goes to numerator, the other number goes to denominator. The numerator is always no more than the denominator. That makes the probability bigger than or equal to 0, less than or equal to 1. And N here is the number of outcomes in the sample space. And the numerator here is the number of outcomes in the sample space that favor event A. Yeah, so please at least write down this formula. This formula is the formula to compute the theoretical probability. Let me explain one more time. Theoretical probability equals K over N. Denominator is the total number of outcomes in the sample space. Numerator is the number of outcomes that favor event A occurring. For example, A here represents rolling a die and get an even number. By using the formula, we should have 3 over 6, or half, as the probability. Denominator 6 is the total number of outcomes in the sample space. Numerator 3 is the number of outcomes that favor event A, right? Event A has 3 outcomes. 2 occur. If 2 occur, then if you get a number 2, then that's even number. If you get number 4, it's also even. If you get number 6, also even. So that's some basics about probability. Let's now go ahead to work on problems. Write a fraction in simplified form. I'll leave those problems to you for yourself to practice. And one thing I can help you is the TI-84 calculator is able to help you to simplify if you really want to advantage of that. So you enter 10 divided by 24 in the calculator, right? And then what do? Let me get my calculator. You enter 10 divided by 24. And then you go to math. And then you see right away in the menu, on top of the menu, under math, number 1 is a fraction. In fact, the item is already highlighted, FRAC. And you enter that. You enter. And enter again. You will get a 5 over 12. So that would be, I would believe that would be very, very helpful for your test. Of course, it's better you know how to simplify a fraction manually. But if you want to help from the calculator, that's how you simplify a fraction by using the calculator or converting a decimal to fraction. And the fraction is the simplified form. Number 2, yeah, it's also simplify. I'll leave that for you. It's multiply by fractions. Multiply 2 fractions. Let's start from question number 5. The set of all possible outcomes of an experiment is called the sample space. Sample space of the experiment. Sample space is represented by the capital letter S. It is a set containing all the possible outcomes of an experiment. My example earlier, rolling a die. The sample space of that experiment would be a set containing all the possible outcomes. Number 1, number 2, number 3, number 4, number 5, number 6. The theoretical probability of event A, denoted by P of E. Sorry, event E. E is the initial of the word event. Is the number of outcomes in E divided by number of outcomes in the sample space, or the total number of possible outcomes. So this problem is about the definition or the formula to compute that we use to compute the theoretical probability. The sum of the probabilities of all possible outcomes in an experiment is 1. This statement is true. Okay? This statement is true. The sum of the probabilities of all possible outcomes in an experiment is 1. It is true. In our example, for example, rolling a die, all the possible outcomes are number 1, 2, 3, 4, 5, 6, right? Each outcome has a probability 1/6. Add them all up, we have a 6/6, that is 1. A 12-sided die is rolled. The set of equally likely outcomes is 1, 2, 3, all the way to 12. Find the probability of rolling a number 9. So in our textbook, we don't really have this concept or definition, theoretical probability model, but I want you please always double check the definition. Always double check. Yeah, exactly. Thank you, Lane. Yeah. Always double check the example is a theoretical model. Consider 2 conditions. First condition, the sample space has a finite number of possible outcomes. Second condition, all those outcomes are equally likely to occur. It will not take you too much time to check the 2 conditions. Once you go through those 2 conditions, you are sure this is a theoretical probability model, then you can safely apply the formula that we have just learned. All right, yeah, please do so. Even for some reason that part isn't covered by the book, we should do that, because we have multiple definitions for probability. And this experiment has a sample space containing finite number of outcomes, and all those outcomes are equally likely. How do we know? Because it says so, right? The set of equally likely outcomes. Yeah, that means the 12-sided die is fair. Each side has the same chance to show up, to appear. Okay, so based on that, we can use the definition. You can use the formula. Denominator is the total number of outcomes in the sample space, 12. Numerator is the number of outcomes favor. Yeah, number of outcomes favor the event. What event? Rolling a number 9. There's only one outcome favor that event. So, my bad. It's not 9. It's 1. Okay, it's 1. There's only one outcome favor that event. So 1/12. Type an integer or a simplified fraction. In this chapter, we have to be careful about the instruction in the parentheses, continually paying attention whatever inside the parentheses. Provide the answer the system asks you to provide. Let's continue. You will see a classical model is pretty intuitive. What's the new things about today's class? New things we learn in today's class about the classical model is you need to be mindfully or consciously to check this is a classical model, and I can use the classical probability formula, and the denominator is the total number of outcomes. Numerator is the number of outcomes favor the event. Let's look at this problem. Same experiment, right? We are looking for the probability of rolling an odd number. So we already checked just now. It is a theoretical probability model, so we can use the formula. Denominator is the total number of possible outcomes, so 12. Numerator is the number of outcomes favor the result. Favor the result or the event. What's the event? Rolling an odd number. Okay, so if we get the number 1, do we have an odd number? If we roll number 3, do we have an odd number? Number 5 also contribute to getting an odd number, right? 7, 9, 11. So 6 of them. 6 of them. And then you simplify this fraction. Simplify this fraction. 6 over 12, we have 1 over 2. A 12-sided die is rolled. The set of equally likely outcomes is that. The same example, same experiment is classical. Find the probability of rolling a number less than 10. Okay. Well, denominator would be the same, 12. Then among the 12 outcomes, how many of them favor rolling a number less than 10? Strictly less than 10, okay? From 1 all the way to 9, those numbers is less than 10. So we have a 9. Yeah, this time we have a 9 as a numerator. And how do we simplify 9 over 12? 9 over 12. To simplify a fraction, we need to divide out the common factor from both top and bottom, right? 9 is divided by 3. Yeah, 3/4, exactly. Very good. How do we know if a fraction is already simplified? When the numerator and the denominator are co-prime, when they have no common factor except 1, then the fraction is simplified. 3 and 4 have no common factor except 1, so it's simplified. Well, we continue have the same model, right? It's classical. This time we are going to find the probability of rolling a number greater than 4, bigger than 4. Denominator still 12. Numerator is the number of outcomes bigger than 4. So we start from 5. 5, 6, 7, 8, 9, 10, 11, 12. So that is what? How many of them? 8 of them, right? Can you help me to simplify? How do we simplify 8 over 12? Divide the top and the bottom by what? By 4, right? Divide 8 by 4, we have 2. Divide 12 by 4, we have 3. So the answer is 2/3. A 4-sided die is rolled. The set of equally likely outcomes is that. So you can quickly double check. Okay, this is a classical. 4 outcomes only, equally likely. Find the probability of rolling a number less than 7. Less than 7. What do you think? Denominator is 4, right? Total number of outcomes. Among the 4 outcomes, how many of them less than 7? All of them less than 7, right? And what is 4 over 4? Exactly, thank you, Lauren. Is 1. So we have a full class today. Yeah, perfect, yeah. Is 1. When an event has the probability equal to 1, we call the event certain to occur. Certain to occur, all right? This is an example of an event that is certain to occur, because when we roll a 4-sided die, you might have not seen a 4-sided die, but we can look at the website. I only saw 6-sided die, the normal cube die. There's a, we can easily get, for example, 12-sided die. Earlier we have 12-sided die. What does it look like? I remember, yeah, right here. 12-sided die look like that, and 4-sided die look like that, like a not pyramid. Is actually not pyramid. Is a triangular pyramid. Triangular pyramid. Yeah, so we can play with it. This is the normal die, right? And this is 12-sided die that we had just seen earlier. So 4-sided die is a triangular pyramid. And when you roll a 4-sided die, and the number definitely is less than 7. So that's something certain to occur. That's the reason the probability is 1. A 12-sided die is rolled. The set of equally likely outcome is that. Find the probability of rolling a number greater than 14. Do we have that? Yeah. So let's apply the formula. It is a classical model, and denominator is 12, numerator. Any of the 12 outcomes favor the result that we roll a number greater than 14. None of them, right? Yeah, none of them. So 0. 0 over 12 gives us 0. Some events, their probability is 0. When the probability is 0, the event is impossible to occur. Impossible to occur. Yeah. When you roll a die, when you roll a 12-sided die, it's not possible to get a number bigger than 14. So 0, okay? You are dealt 1 card from a standard 52-card deck. Find the probability of being dealt a 6. I had the students that telling me that I have no idea what is poker, because I do not play poker at all. You know what? If you are not familiar with what is a poker, just check it, right? Standard deck of cards. It looks like that. Let's see, what do we have in a standard deck of cards? Let me look at this picture. In a standard deck of cards, you might wonder, when we learn theoretical probability, why there are so many stuff from the casino, right? You know why? It's because the definition, yeah, because the theoretical probability originally come from the gambling industry. That's the reason. Yeah, I can say almost all the games in casino, they should give you a classical model. Most of them. Yeah. So this one, let's see what this picture. We have 52 cards, okay? We have 52 cards in total in a standard deck. We divide the 52 cards into 4 suits, S-U-I-T. The 4 suits are, what's this called? This is a space. Yeah, this is space. This is hearts. This is clubs. This is diamond. Hearts and diamond are red color. Club and space are black color. So half of the cards are red, half of the cards are black. In each suit, we have 13 cards. From 1, yeah, they put a 1 here, but actually we see 1 as a number card. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 number cards. J is 11. Q is Queen is 12. Yeah, Jack is 11. Queen is 12. King is 13. So J, Q, K, they are face cards because they have a person with face, right? Face cards. So each suit we have 3 face cards. The rest of the 10 cards are number cards. So in total we have 12 face cards, right? Yeah, so that's what it looks like. A standard deck of cards, 52 in total. So this problem, you dealt 1 card from a standard 52 card deck. Find the probability of being dealt a 6. You know, we have to see if this is a classical model, right? If it's a classical model, what is the sample space? We can see the experiment as take a card from the deck and write down the number. If the experiment is to observe the number, then the sample space would contain 13 possible outcomes. Because either you get the number 1 or get the number 2 all the way to number 13, right? Yeah. So the sample space should contain 13 outcomes. So the denominator is 13. And it is classical because each number has 4 cards. So each number has an equal chance to occur. It is equally likely. So denominator is 13. And among the 13 outcomes, possible outcomes, how many of them favor dealt a number 6? Let me write down the sample space actually is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This is the sample space, okay? Only one of them favor the event. So it's 1 over 13. 1 over 13. Yeah, okay? We have 2 ways to do this problem. Or you can see the sample space contains 52 different cards. Each card has an equal chance to be dealt, right? And among the 52 cards, how many of them favor number 6? If we look at the website, how many number 6 do we have? We have 1, 2, 3, 4. 4 number 6, right? From each suit. So the numerator is 4. And if you simplify 4 over 52, you get 1 over 13. Same thing. But use this sample space, the problem becomes a lot easier. Yeah, either way is correct. Either way is correct. I explained that clearly in my video. Okay. Same experiment. This time we are picking a card, randomly pick a card from the deck and observe what type of card it is. So in order to guarantee, to ensure the experiment is a classical model, this time we are going to consider the 52 cards as the sample space. Yeah, we have 52 cards in total, 52 different cards in total, and they have the same chance to be taken. Among the 52 cards, how many of them favor the event? The event is getting a non-picture card. A picture card is like a face card. The non-picture card. Tell me how many non-picture cards we have. Each suit we have 3 face cards or picture cards. We have 10 non-picture cards. 4 suits, we should have 40 non-picture cards, right? So the numerator is 40. Yeah, I'm showing you quickly the picture. This. So number 1, number 2, number 3, all the way to number 10. Yeah, those are non-picture cards. So we have 40 non-picture cards in total. Okay, how do we simplify this fraction? So if we divide 52 by 4, we have 13, right? If we divide 40 by 4, we have 10. You divide both top and the bottom by 4, we have 10 over 13. You are dealt one card from a standard 52 card deck. Find the probability of being dealt a card greater than 5 and less than 10. And which sample space is more convenient? Since the result is about number, we would consider this as the sample space, right? Number 1, number 2, all the way to number 13. And they are equally likely, is a classical model. Among the 13 outcomes, how many of them greater than 5 and less than 10? Knowing greater than 5 does not include 5. We start from 6. 6, 7, 8, 9 does not include 10. 10 is not less than 10. So 4, right? 4 over 13. 13 is a prime number. 4 over 13 is already simplified. A fire coin is tossed 3 times in succession. The set of equally likely outcomes is that 1, 2, 3, 4, 5, 6, 7, 8. If we use the fundamental counting principle, we would know the sample space should contain 8 possible outcomes. Yeah, because you are toss a coin 3 times, right? Yeah, this is how do we record the result from the 3 times. We have 2 possibilities. If you toss the coin the first time, you either get a head or you get a tail. 2 possibilities, right? And the second time you flip the coin, you either get a head or you get a tail. The third time you flip the coin, you either get a head or you get a tail. 2 times 2 times 2, you get 8. But it's given for the in the problem, 8 possible outcomes are equally likely. Is given equally likely, but from symmetry, we should also be able to tell they are equally likely. So this is a classical model. We need to find the probability of getting 2 heads. Denominator 8. 8 possible outcomes in total. Numerator, how many of them favor the event? 2 heads. Let's count it. This one has 3. No. This one has two heads, right? So 1, 2, 3. That's it. Because this one has 1 head, 1 head, 1 head, and no head. So 3 of them has 2 heads. 3 over 8 is simplified because 3 is prime and 8 is not divisible by 3. 3 and 8 are co-prime. Yeah, that part belongs to algebra class. In case you are not comfortable with the fraction, just now I told you how do you use the calculator to get a result, right? A fair coin is tossed. Okay, the same is two times. 2 times, so we have 4 possible outcomes in the sample space, and they are equally likely. It's a classical model. Find the probability of getting exactly 1 head. Denominator 4. Numerator, how many of them getting it has only 1 head? The second one and the third one, right? We have 2 of them exactly has 1 head. This one has 2 heads, this one has 0 head. So 2 over 4. 2 over 4 simplify. We get half. please do not enter 0.5 because the instruction says type an integer or a simplified fraction. 1/2. This experiment is to roll a die twice. Roll a die twice. And we can record the result this way, right? It's the first time, the second time. You roll the die the first time, you have 6 possible results, right? And you roll the die another time, you have 6 possible results. So 6 times 6, we got 36. So we have 36 possible outcomes in the sample space. And we use a ordered number pair to record the result of the outcome of the experiment. For example, 1, 1 here represents the outcome that the first time we get the number 1, second time also get the number 1. And if we look at this outcome 4, 5, it represents the outcome that the first time we get the number 4, second time we get the number 5, right? And this one means first time we get the number 6, second time we get the number 3. This outcome means the first time we get the number 6, the second time we also get the number 6. They are equally likely, not only because the problem specifically states that, also because of the symmetry, okay? The die is fair. Based on the symmetry, the 36 outcomes are equally likely. So this is a classical model. I mentioned this example in my video. We are looking for the probability of getting 2 numbers whose sum is 11. Okay. So in my video, actually, I mentioned this. Okay, so I'm going to do this. Give me 1 second. See if the internet today support me to copy paste. Uh-oh. Try one more time. No. Copy. Paste. Okay, so we are talking about the sum of the 2 numbers, right? I want to show you the pattern. Look at here. We have 1 outcome. The sum of the numbers is 2. And look at those 2 numbers. Let's look at those 2 outcomes. Those 2 outcomes, for both of them, the sum of the 2 numbers is equal to 3. And look at those 3 outcomes. Those 3 outcomes, the sum of the 2 numbers equal to 4, right? 3 plus 1, 2 plus 2, 1 plus 3 equal to 4. And those, you should see the pattern now. Those 1, 2, 3, 4 outcomes, sum of the 2 numbers equals 5. And those outcomes, sum equals number 6. Those outcomes, sum equals number 7. Those outcomes, sum equals number 8, right? 6 plus 2, 5 plus 3, 4 plus 4, 3 plus 5, 2 plus 6, they are all equal to 8. And those outcomes, sum equals 9. And those outcomes, sum equals 10. Those 2 outcomes, sum equals 11. 1 outcome, sum equals 12. Do you see that? Do you see that? So among the 36 outcomes, how many of them have the sum of the 2 numbers equal to 11? Let's see, 11. 11, so this one, right? Those 2, yeah. 6, 5, 5, 6. So we have two outcomes. Sum is 11. 11 over 36. 11 is prime. 36 is not divisible by 11. So that is already simplified. Hold on. Oh my gosh. 11. Why did I do that? I have two outcomes. Sum is 11, right? Enter 11. Okay. Two outcomes. I apologize. Two outcomes. Sum is 11. So 2 over 36. Simplify. We have 1 over 18. 1 over 18. Same example or same model. This time we find the probability of getting two numbers whose sum exceeds 15. Whose sum exceeds 15. Earlier I just shown you, right? Yeah, sum over here is 2, and this is 3, this is 4, 5, 6, 7, at most 12, right? The sum go beyond 15. That's not possible. It's not possible. We know if the event is not possible, the probability must be 0. All right. So when you see something like that, that means it's gonna be empirical. All right. It's gonna be empirical probability. So let's look at the problem. The table shows the distribution by age and gender of 30.3 million people in a certain region who live alone. Use the data in the table to find the probability that a randomly selected person living alone in the region is male. Okay, so let's consider our experiment is to randomly select a person from the 30.3 million people who live alone, okay, in a certain region, who live alone. Let me repeat the experiment. Randomly select a person from the 30.3 million people in a certain region who live alone and record the person's gender. Then how many possible outcomes do we have? We would have two outcomes, right? Either female or male, correct? Well, finite number of outcomes in the sample space. However, are the two outcomes equally likely? Are they equally likely? Huh? They are not, right? Do you agree? It's not. Yeah. Yeah, they are not equally likely. Thank you, Lian. So it's not classical, okay? We only learn two models. If it's not classical, then it must be empirical. Then how do we compute empirical probability? And we have a formula. The formula is similar. Let me see how do I get rid of this stuff. How do I get rid of that? Okay. So empirical probability. Same formula but different meaning, okay? K is the total number of subjects you survey. And K is the number of subjects who favor the event. It's actually a frequency, relative frequency. Once we work on a few questions about the empirical probability, you would understand. So let's see how do we process this problem. is also a fraction. To find the empirical probability, we also need to find the two numbers. One goes to the bottom, the other goes to the top. The number goes to the bottom is the total number of subjects that you survey. So you survey 30.3 million, right? So 30.3 is going to be the denominator. And numerator is going to be, among those 30.3 million people, how many of them, how many of them are male? How many of them are male? How many? 13 of them are male, right? To solve this type of problems, you need to be able to understand the table. And let me know, anyone have trouble to see what's going on in this table. So in this problem, we only need to look at the table horizontally. Horizontally. The total number of the subjects is 30.3 million. And among the total 30.3 million people, we have 17.3 female, we have 13 million male. That's how we look at the table. So 13 over 30.3. And then look at the instruction. Type an integer or decimal, round to the nearest hundredth as needed. Follow the instruction, please. Let's see what we have. Use a calculator. Divide 13 by 30.3. If I, by the way, the decimal as a probability must be bigger than or equal to 0, less than or equal to 1 as well, always. So if you get a result 1 point-ish or 2 point-ish or 10 point-ish bigger than 1, that means it's wrong. So we run it to two decimal places. We would have 0.43. This is the same table, right? But this time, our experiment is different. Even it's not specifically tells you the experiment, you need to be able to describe what kind of experiment this is. So this experiment is you survey 30.5, 30.5 different number, 30.5 million people, okay, who live alone in a certain region. And you are going to write down those people's age or age categories. You have 1, 2, 3, 4, 5, 6 age categories, right? 18 to 24. So only adults, not kids. Kids probably shouldn't live alone. That's true. Okay, second category is from 25 to 34, and 35 to 44, 45 to 64, 65 to 74, and older or equal to 75. So we have 1, 2, 3, 4, 5, 6 categories, right? So your sample space should have 6 possible outcomes. You survey all the person live alone and write down their age categories. So you have 6 outcomes. However, those 6 outcomes definitely not equally likely, because they are not uniformly distributed, right? Definitely not. Depends on the region. Definitely not equally likely. So this is not classical. It has to be empirical. Knowing if you have something like that, a table, it must be empirical. Then the denominator would be the total number of people you survey. In this case, 30.5. And numerator would be the number of people who fall in this age category, 25 to 34. How many people fall in? How many people aged from 25 to 34? 4.1, right? Do you think you can see that? Age 18 to 24, total is 1.6. Age 25 to 34, total is 4.1. 4.1 is the number we are looking for. And then we use a calculator to compute convert to decimal, round to the nearest hundreds. We divide 4.1 by 30.5, round to the nearest hundreds. So run it down, 0.13, 0.13. So by the way, yeah, be careful, don't enter O as 0. Yeah, O and different from 0. So 0.13. It always be 0 point-ish, 0 point-ish. Okay. And one more question. Okay, let's go do one more question. Same experiment, same setup, same setup. This time we are recording the person's age group and age, and gender. Okay, so we survey, so it's empirical for sure. The denominator would be the 28.9. 28.9. I want you to help me to find the numerator. Okay, among the 28.9 million subjects, how many of them are women and age between 18 to 24? Women, female, okay, women and age between 18 to 24. You help me to find the number in the table, and the number is gonna go to the numerator. Yeah, look at the table and tell me what you have. Awesome, thank you, Liam. Do we agree, other classmates? Do we agree? Yeah, I got that as well. Perfect. Yeah, 0.5. Perfect. Very good.
Yes, I got that too.
Yeah, 0.5. Perfect. Yeah, 0.5. Yeah, it is the intersection of row women and the column 18 to 25, right? Is right here, 0.5. Let's do the division. 0.5 divided by 28.9. How do we round to the nearest hundreds? 0.0017. So round it up, 0.02. 0.02. All right. So that's today. We covered 2 definitions of probabilities, theoretical and empirical. How do we find the value of a theoretical probability, and how do we compute the value for a empirical probability? So that's today. I would say tomorrow is the last day to take test 2. Please be prepared. And once you get the test 2 done, you have to quickly get into the new chapter and get ready for test 3. Yeah, again, this is a very fast-paced class. I know it's kind of challenging. Again, I hope you watch my video, because when I look at the usage of the video, it's very low. It's pretty low. I feel very sad. I don't know how people learn without the you know, they are reading the books. I don't know how. If you have any questions, you are welcome to email me anytime. Okay. I'll see you on Monday. Have a good weekend. Bye bye. Thank you for coming.